Okay. We're going to do a reminder, kind of a quick review on what we went over last week, because it's been a minute and sometimes I can't remember what I did yesterday. Is lab in person this week in the chat? It's online. So we're meeting on Zoom this week, and next week you're going to come to lab in person for the vinegar titration. But this week we are meeting online on Zoom for the chromatography lab. Great questions. All right, let me go back. So we worked, you guys remember this slide right here? It's kind of where we ended. Right here, units of concentration, weight volume percent, molarity, moles per liter. And then we worked several problems on this. So we defined last Thursday, we defined what a solution is, solvent, solute. We talked about guidelines for solubility. You guys remember the principle like dissolves like. Polar solutes dissolve in polar solvents. Same for nonpolar, but things that are polar and nonpolar, they don't mix. We talked about how you can manipulate solubility with temperature. Somebody remind me. If you have a solid dissolved in a liquid, a solid in a liquid, and you increase the temperature, okay, you heat it up. Will you increase solubility or decrease solubility? If you have a solid dissolved, like sugar in water or salt in water, Tyler says increase. Yep. Okay, that had to do with these graphs right here. There's actually one of these on your homework. So student was just asking me about a problem where you have a solubility graph on the homework, okay? And I'm gonna make a note of this real quick. We really don't have time, but this is gonna help you on your homework. Okay, there's a homework problem. And it tells you something like this. It says, oh, you got 15 grams of NaNO3 per 20 ml. Okay, so this number, the number of grams might be different per 20 ml. And then it says, you know, like 60 or 50 degrees Celsius is the solution, saturated, supersaturated, or not saturated. That's the homework question on your homework. I don't know which number it is, I forget. But notice over here, if you look at units, this unit is per 100 ml. So if you're trying to make a judgment call, you can't judge this number per 20 ml. What do you need to do? Anybody have an idea? Make a note of this. It'll help you on your homework. You need to multiply this by 5, okay? By 5. You need to judge it per 100 mLs, okay? Because this is per 100 mLs. So multiply whatever number it gives you on your problem by 5, and then you can make an accurate comparison. Okay, at 60, what just happened? So NaNO3 would be the purple line. So I'd take my whatever temperature it is, run it up to my line, and then walk it over. I know my solubility, it is saturated at around 120 grams per 100 ml. So then you multiply it by 5 and you look at what it tells you in your problem. Is that more than 120, less than 120? Okay, and you judge if it's saturated or supersaturated or not saturated based on that comparison. Does that make sense? That'll help you on a homework problem. Okay, anyways, we looked at those trends. We looked at gases as well. It was all last Thursday, and we talked about Henry's Law. There's another problem on there with Henry's Law. It's talking about like a soft drink at different pressures. That's a challenging one too, but that is all a Henry's Law. I think this is 9.39 on your homework. In fact, I know it is. That is a Henry's Law problem. Okay, reach out to me if you have questions on that one. Anyways, we did all that, and then we worked a lot of problems. So that's where we ended, and we're going to work one more problem because we did not do one yet with molarity, and then we're going to move on to kind of the next topic in chapter 9. So if you dissolve, here's the problem, 2.335 grams of H2SO4 in water, and you dilute it to 50 milliliters, what is the molarity? Okay, our equation for molarity, we abbreviate molarity with an M, is moles of solute per liters of solution. I don't have moles or liters yet. Dadgum, we got to do a lot of conversions before we can plug anything in. We need to convert grams to moles first using a molar mass. We need to convert milliliters to liters. Then we can plug everything in. All right, so let's get a molar mass for H2SO4. We got hydrogen, sulfur, and oxygen. You guys remember how to do this? We got 2 hydrogens. You grab the number off the periodic table, the mass number for hydrogen is that. Sulfur is what? 32. I think that's what we used this morning, 32. Are there any important decimals with that? Has Grayson already calculated it all for us? Okay, and then oxygen would be 4 times 16 grams. Okay, you add all this up. Grayson said she got 98 grams. Is that what y'all got? Any decimals there? 2 times 1.01, 1 times 32, and 4 times 16. Oh, not 94, 98. Anybody get something different? I'm going to assume it's this. All right, now let's convert the actual number of grams, 2.335, to moles using that molar mass. So we want grams to cancel. So for every 98 grams of H2SO4, it's 1 mole. So how many moles?
Hello. Greetings, big sister.
Oh, somebody needs to be muted again. Oh no, I always get nervous when this happens now. Okay, 0.0238 mole H2SO4. I'm having flashbacks, guys. Anybody having flashbacks to that one fine day? All right, that's how many moles H2SO4. Okay, and then we need to convert milliliters to liters. So 50 milliliters. We know there's 1,000 milliliters per 1 liter, and that should give us 0.05 liters. All right, so now we can divide both of these and calculate a molarity. Okay. So we'll do 0.0238 moles. Don't make me laugh, everyone. Stop. 0.5 liters. All right. 0.0238 divided by 0.05. What is our molarity? Oh, Grayson. Does everybody agree with Grayson? 0.48 molar? Yeah, and it's molar, right? And again, this, or you could write it 0.48 mole per liter. Okay, that's what molarity is, a moles per liter. Very similar to like molar mass, which is grams per mole. Okay, but this one's mole per liter. All right, questions on how to solve for molarity. So on the exam 4, definitely expect a problem where you're calculating a molarity. Definitely expect a problem where you're either calculating a weight volume percent, or I give you the weight volume percent and you're calculating like either the grams of solute or milliliters of solution. Okay. But I want to point something out real. So we got moles per liter. Anytime we have a relationship like this where we're relating 2 units, density was 1, mass and volume. Molar mass was 1. We can always use that as a conversion factor. So that's the next kind of problem we're going to work. We're going to use molarity as a conversion factor. And this little tool right here is going to allow us to build to work an even more difficult style of problem, which is another like 3-part problem. You guys remember the 3-part problems from chapter 6? We're going to work another one of those, but this time using molarity. So first, let's read this problem right here. A blood alcohol content of 0.065 molar is enough to induce a coma. Hopefully none of you have been there. If the total blood volume of an adult male is 5.6 liters, then how many grams of alcohol, this is ethanol, C2H6O, are necessary to reach this concentration? Some of you are way too eager to know the answer to this. All right, we're going to start with how do we answer this problem? What's given? Well, we're given, I'm going to highlight it, the volume of blood, 5.6 liters. That's where we're going to start. And we're trying to determine how many grams. So we're trying to go from liters to grams. So we don't have a way to go directly there. We can't do this in one step. But we can use molarity, and that's what it says here. Use molarity to convert to moles of, what is ETOH? This is ethanol, okay? The C2H6O, that's ethanol. ethanol is alcohol. Any alcohol bottle you buy will tell you what percent ethanol or alcohol it is, right? And then you can use the molar mass to convert 2 grams from moles to grams. So we're going to go from liters to moles. Then we're going to use the molar mass of ethanol to go from moles to grams. So this is a 2-step problem. So start with the 5.6 liters of ethanol, or no, blood. Okay. And what this molarity says, I'm going to zoom in on the molarity for just a second. This is what it's saying is 0.065 moles. Moles of what? Moles of ethanol. Per liter, what's the solution here? Liter of blood. Okay, that's what this actually means. An alcohol content. That many moles of the alcohol per liter of your blood is the solution. Okay, alcohol, it would be in your blood. So that's what we're going to plug in. We want liters to cancel. So for every 1 liter of blood, if you have 0.065 moles of ethanol, you are in danger. This is probably a dumb question, but is the alcohol in drinks the same type of alcohol in medical rubbing alcohol? I'm actually not sure what type of alcohol is in medical rubbing alcohol. Anybody want to help us out with that? Possibly. I mean, ethanol would be disgusting. You would not want to take a drink of ethanol, but that is what is in isopropyl. That sounds about right. Isopropyl alcohol. I think that somebody could Google it. I think it might be different. I don't know if you could just go buy a bottle of ethanol straight off the shelf. Yeah, so I think they are different. Probably has the same results. Probably one way to find out. Oh gosh. All right, back to our problem. So now this is step 1 where we have plugged in the molarity. Okay, and you see how we've used it to convert? What did we do? We canceled liters, okay? But we want grams and not moles, so we need to know what the molar mass is. We're going to plug in the molar mass. So for every 1 mole of ethanol, how many grams of ethanol is that? I have seen an alcoholic man drink hand sanitizer. Oh my gosh. That's drawing the line. I'm drawing the line. That's too far. All right. What is the molar mass of ethanol? That's what we're trying to do. You guys are distracting me. So we got carbon, hydrogen, and oxygen. We've got 2 times 12. If you don't have the molar mass or the mass of carbon memorized yet, you haven't been paying attention enough in this class. And oxygen 1 times 16. So you multiply all this, 2 times 12.011, 6 times 1.01, and 1 times 16, because you got 1 oxygen. So total, what is that, 48 point, is that what you got? 48.082. So that's the molar mass. And so then you'll plug in that number of grams. And look what happens. Moles of ethanol cancel. So we've used molarity to convert from liters to moles. Then we use molar mass to convert from moles to grams. So how many grams of ethanol would that be? 5.6 times 0.065 times 48.082. 17.5 grams of ethanol. Now, obviously, in drinking alcohol, that you're not drinking straight ethanol, okay? So it would take a lot more alcohol than just 17.2 grams. Okay, any questions on how you can do a simple conversion with a molarity? Does it help if you write it out like this right here, mole per liter, and that way you can see which way to plug it in. That should help. That's what I recommend you do. Anytime you see this capital M, you can write it out as mole per liter. Okay, the next thing we're gonna do is I'm gonna introduce the three-part problem with molarity stuff. So you guys remember chapter 6, I know you remember, three-part problems where we would be given a mass of like reactant A or B or product, whatever, and we're trying to figure out the mass of another reactant or product in the balanced chemical reaction. And you would always plug in the molar mass of substance A, then the mole ratio, and then the molar mass of substance B. Okay, whatever you're trying to convert to. It's the same idea here, but we're using molarities instead of molar masses. So if we have this balanced chemical reaction right here, A and B makes C and D. So what kind of problem, what kind of question would these would apply here? Let's say you're given like 1 liter of substance A, and you know the molarity is 0.5 molar. And then you want to know what volume of B should I react with this solution of A. I know my molarity of substance B is 0.25 molar. Okay, this is the kind of questions. Okay, it'd be a full-on word problem, but at the heart of it, this is the style of question. So what you're given, look, you are given the volume and the molarity of substance A. So you're going to start with the volume. And step 1 is you're going to use the molarity to convert from liters to moles. Okay? From liters to moles. So in this step, you're going from liters to moles. And that's because molarity equals moles per liter. Step 2 is you're going to use the coefficients in the balanced equation to get a mole ratio. Y'all have done this so many times. Okay, so that should not be anything surprising or confusing how to do a mole ratio. Once you've gone from moles of A to moles of B using the mole ratio, the last step is you're going to use the molarity of substance B to convert from moles back to a volume, because the questions ask for what volume. All right, so we're going back from moles here to liters using the molarity, which is again mole per liter, but for substance B this time. Okay. So that's the problem in its entirety. We're going to work one like this right after you guys finish writing this down. All right. You got it down? So let's look at an example. I want to skip over the next slide because it's actually not it gives you milligrams instead of volume, and that really doesn't fit. It's a good problem to work, but let's do the next one first. Right here. All right, we got a word problem. We're going to have a balanced chemical reaction, obviously, to get a mole ratio. So as you read the problem, try to write out the balanced reaction. It says calcium carbonate reacts with hydrogen chloride, hydrochloric acid. So these are your two reactants. So what is the formula for calcium carbonate and hydrochloric acid? Calcium carbonate. Carbonate is a polyatomic ion. You guys remember those? All right, so anybody know the formula? Calcium carbonate, CaCO3, plus HCl, and they react to make calcium chloride. What would that be? Obviously calcium. How many chlorides do I need? Thank you, Kennedy. plus water, H2O, and CO2. All right, there's our reaction, but it's not balanced. So what coefficients do we need where to balance this? 2 HCl. And then I think you're good. 1 calcium on each side, 1 carbon, 3 oxygens on each side. Yep. 2 hydrogens, 2 coins. Okay, so we're balanced. How nice. All right, here's where the question begins. Let's highlight this. How many milliliters of a 0.22 molar solution of calcium carbonate? So here's what I notice. I'm asked for the volume, and I'm only given the molarity. So this is what we're going to try to find, the volume of calcium carbonate. How many milliliters are needed to react completely with 25 milliliters of 0.5 molar solution hydrochloric acid? So we're going to call HCl substance A, CaCO3 substance B. Just if you're, for the sake of, how things were labeled on the diagram earlier, A to B. That's because we're given both a volume, that's the volume, and a molarity for HCl. So we're going to start with the volume. Remember the diagram. Let me scroll up. I'll come right back. We start with the volume of solution A. And then the first thing we do is use the molarity. So we're going to use those first 2 numbers right off the bat for HCl. All right. So 25 milliliters, but hold on. What do we have to do first? We can't convert milliliters. Molarity is mole per liter. Okay. What this says, oh, that's not eraser. Bradley says change it to liters. Yep, that's right. So this is 0.5 mole per liter. So I can't use milliliters. I got to convert it to liters. So for every 1,000 milliliters, it's 1 liter. All right, I can use this now, 0.025 liters. Okay, so I'm going to use molarity, convert to moles. That was step 1 of the 3-part problem. So I want liters to cancel. So for every 1 liter, it's 0.5 moles of HCl. Please label your compound here. Liters cancel. Why do you need to label HCl here? Because when you plug in the mole ratio, some people will accidentally flip it and put the wrong mole ratio part on the wrong part of the factor, conversion factor, if your compound isn't labeled. So this was step 1. We plugged in the molarity of HCl. Step 2 was what? What do we need to do next? Yep, mole ratio. So what is our mole ratio? We're looking at HCl and CaCO3. 1/2. That's exactly right, Tyler. For every 2 moles HCl, it's 1 mole CaCO3. So that was step 2, mole ratio. And then lastly, we need the molarity of substance B, which is our calcium carbonate. What's the molarity of that? What do I need to write in? What goes on bottom? What goes on top? I'm trying to convert back from moles of calcium carbonate to a volume. We can only go to liters. Okay. Tyler says 0.22 on bottom. What are the units? Mole. CaCO3. I ran out of space. For every 1 liter. That is what this molarity right here means. Okay. 0.22 moles per 1 liter. Yep. Thank you, Keegan. Okay. So this will get us to liters, and then the question says how many milliliters. So we'll convert that back to milliliters in the end. So technically it's like a 5-part problem, right? What is our answer though? So you're going to start with 0.025 times 0.5 divided by 2, and then divided by 0.22. As a reminder, I encourage everybody, be working this problem with us, grab a pencil, be writing this out with us. Don't just watch me do it. It'll help way more if you do it with us. Okay, Tyler says, Keegan says, so far seems like it's 0.028 liters. Okay. And then if you convert back to milliliters, so for every 1 liter, it's 1,000 milliliters, you should get 280. So maybe it was 0.0284. So if you had the 4 in there as well, but should be right around 280 milliliters, okay? Okay, this is a hard problem. This was a long problem. This could certainly be a file response question on exam 4. Questions on this? This is going to take practice to get comfortable with this. So there's definitely there's some homework problems. I don't remember which ones. On your chapter 9 homework, there's a few that are like this. Any questions on this? I feel okay with it? Seeing some head nods? Okay. All right, well we're gonna put a pin in that. So that's one topic for today, molarity as a conversion factor. And we're gonna move on to a different aspect of solutions. So all of chapter 9 is on solutions. And we need to talk about the fact that sometimes you have to dilute solutions. And this is a familiar concept. You know what diluting is. But there's an equation that represents how you go about this. So you already are probably aware there's lots of equations with chapter 9. So here's my recommendation. Get a little index card for the exam and write down all the equations. Write down your weight volume percent, write down your equation for molarity, write down your equation for dilutions, and label them. That way, when you get to a problem on the exam 4, and you read it and you have no idea where to begin, there should be some keyword in there like diluting or what is the percent, and that should tip you off on what equation to use. Okay. That's just my you don't have to do that, but that's just my recommendation because we have so many different equations. But all right, dilutions, especially true for clinics or hospitals. When you order things and you typically get a solution that is more concentrated than you would need. And we call this a stock solution. All right, they're more concentrated than we need. So to use it at an appropriate concentration, you have to dilute it. And you're diluting it to what you call the working concentration. And that's what you're going to use. That's what you're going to actually administer to the patient, or that's what you're going to use in the lab or whatever. So then the question is with dilutions, well, how do I dilute properly? How much solvent do I add to dilute it? How do I know what concentration I'm going to get? Well, you can use this equation, M1V1 equals M2V2. This looks a whole lot like Boyle's law, right? Which was P1V1 equals P2V2. So this is just slightly different. M standing for molar concentration. So it's a molarity. And then V, the volume. So you can actually work these volume. You can work them in milliliter or in liters. Does not matter, but you cannot work it in milliliters and liters. Okay, you can't have like your V1 in milliliters and your V2s in liters. They have to both be same units, but it doesn't matter if they're liters or both milliliters. That make sense? Okay. All right, so actually, I think that's it for this slide. We're gonna look at the next one and just work a problem or two as an example. Okay, first one. So I have 75 milliliters of 3.5 molar glucose. I dilute it to 450 milliliters. what is the new concentration? So here's what I suggest. Let's just label this. The first thing you're given is a volume, so I'm just going to call that V1. And then the first molarity you're given, call that M1. The second volume, V2. So what's the new concentration? So you're looking for M2. So rearrange your equation, get M2 by itself, then plug all your numbers in. So we got M1 V1 equals M2 V2, and we got to divide both sides by V2. So M2, now we're just going to plug everything in. M1 is the 3.5. Both units for volume are in milliliters, so that's fine. I'm just going to leave them there. Times 75 divided by 450. All right. 3.5 times 75 divided by 450. What do y'all get? What would the new concentration be? Haley says 0.583. Yeah, good. Danielle says that too. And that's units of molarity. All right, not too bad. Let's do another one. I can buy 1 molar NaOH. What is NaOH? You guys remember NaOH when we talked about acid-base reactions? We're going to talk about NaOH a whole lot in chapter 10. Sodium hydroxide, it's a strong base. I need 750 milliliters of 0.32 molar NaOH. How do I prepare this? So what pieces do you have here? This is M1, right? And then I need, this would be M2, and this would be V2, because this is the volume associated with, just because it's the first volume given doesn't mean it's a V1. 750 is the volume associated with the second concentration, so that makes it V2. So we're looking for V1. How much of my initial stock concentration do I need to take and then dilute to 750 milliliters? So we're solving for V1. So rearrange your equation. M1 V1 equals M2 V2. So you're going to divide both sides by M1. And then it cancels on that side. All right, so V1 equals 0.32 times the 750 milliliters. So I've just plugged in M2 and V2 divided by M1, which are just, how nice, just 1. Okay, Danielle got 240. All right, 240 milliliters. And it's milliliters, right? Because that's what your units on your other volume are. So there's no way this could be liters. It's got to match. So how would you prepare this? You would take 240 milliliters of your 1 molar sodium hydroxide, and then you would add solvent and dilute it until you have 750 milliliters. And then you would know, okay, now my concentration is the 0.32 molar. Questions on dilution problems? That's it for dilutions. You totally have one of these on the exam. Okay, next topic, if there are no questions. Told you have a lot to cover today. Next topic, electrolytes. We're familiar with electrolytes. We introduced this word formally back in chapter 3 when we're talking about ions, because that's the biological word for ions, right? Electrolytes. So these are ions dissolved in a solution. We call them electrolytes because that solution can now conduct electricity. Sometimes only very weakly, sometimes pretty strongly, but next bullet point, once ionic compounds are dissolved into their ions, we talk about the ions and not the compounds. This is especially true for blood. For example, consider the 2 pictures I have down here. If I add totally different compounds to these beakers. So I've got sodium chloride and potassium bromide for the first one. The second one, I have sodium bromide, potassium chloride, 4 different compounds here. But once they're in solution, what do you get? Well, everything's going to dissolve. So I would get sodium. Now I would get some chloride. I would have some potassium. And then I would also have some bromide. And that's all going to be floating around in solution. Well, what about the second beaker? Same thing. Once everything breaks up, you just have all the ions. So look, it's going to look the exact same down in the beakers. You wouldn't even be able to tell me which ones had which compounds added because everything's the same once it's all dissolved. And we're just now talking about the amounts of sodium and chloride. We're just talking about the electrolytes and the levels there. So going back to this idea that some solutions can conduct electricity strongly or weakly. Well, that's because you have different levels of electrolytes. I'm going to scroll down. You have strong electrolytes, weak electrolytes, and things that don't form ions. So they're called non-electrolytes, but they're still in the blood or different biological solutions. So how do we differentiate? How do you know when something's going to form a strong electrolyte? Well, and this is directly out of your textbook, by the way. I always encourage you, go read along in the textbook, the different sections that correspond to our lectures. So section 9.8, you see this figure. If a strong electrolyte will completely ionize, okay, completely dissolve into its ions. So we're going to get a single arrow, one direction on the reaction here, okay? So you're going to have all ions. You'll have none of your sodium chloride left. It'll all dissolve into ions. That is a strong electrolyte. Okay, unlike a strong electrolyte, something like acetic acid is a weak electrolyte. Why? Because it only partly ionizes into its ions. So we indicate this with a reaction using a double arrow. It will dissolve, you'll get the forward reaction, but then some of those ions will also remake the initial product. So you'll have some of your combined, as actually your molecule of acetic acid. That compound will be in the solution as well as the ions, the dissolved ions. And it'll reach some kind of equilibrium, of course. All right, what about a non-electrolyte? You can identify something as a non-electrolyte when you don't get any ions, okay? Glucose is a great example because, okay, you could have a solid chunk of glucose when it's glucose, oh, I'm not in. The AQ here just means individual glucose molecules, okay, not ions. So I'm going to draw a little picture to illustrate. Maybe you have each individual sphere is a molecule of glucose. As a solid, this is what solids look like, right? They're bonded close together, okay? But when it's in water, if it dissolves, now these individual glucose molecules are just separated, okay? And then they're fluid, they can move around. So that would be, but nothing's ionized. There's no charges. Okay, glucose is just still glucose. You haven't broken apart the glucose molecule. And that's how a lot of biological, fructose, sucrose, anything like that, we would call that a non-electrolyte. So I'm going to run a poll question based on what we just talked about. And I want to know how well you guys feel about this. So electrolytes. Look at solutions 1, 2, and 3. Can I zoom out? See the whole slide? All right, solutions 1, 2, and 3 down here on the bottom. Which one is a strong electrolyte? Which one's weak? Which one's a non-electrolyte? I'll turn my space heater off. Okay, we're only 58% voted. No math to do here, so you're kind of just looking at the examples above. So I'll give you about 15 more seconds. Matt says, so in a non-electrolyte, it will always be solid to aqueous. Yes. Well, it will always, just go on the basis that it will not form ions. Okay, I don't want to say it will always be solid to aqueous, but it will never form ions. Okay, you will not get any ions when it dissolves. All right, in the poll. Okay, so this is what you guys said. Most people, solution one, said a weak electrolyte. You got the double arrow here. Okay, so you're going to get some kind of equilibrium. So this matches for sure what we said with acetic acid. So yes, this is a weak electrolyte. You will get some ions, but it's not going to completely dissolve into only the ions. We don't have a single arrow. All right, insulin into something that's aqueous. I don't see any ions here on either side. So no ions means a non-electrolyte. And 3, so that's what most people said, non-electrolyte for 2. Most people said a strong electrolyte, and you got a single arrow, so you get all ions. No initial reactant left over at the end. So this is definitely strong. Okay. All right, so that's electrolytes. Now we're going to keep talking about electrolytes, but from the standpoint of measuring their levels in like biological solutions. Okay, so how would we go about measuring levels of electrolytes in a biological solution? Well, that's what we do when we're talking about equivalence. Anybody heard this word before? If you have a job like in a hospital, maybe you have. Milli equivalence in particular, which would be MEQ, milli equivalence. Don't confuse E with a capital Q here, okay? E capital Q is equilibrium, something totally different. E lowercase q is equivalence, all right? Keep those. I know it's the same letters, so that's tricky, right? But we're talking about E lowercase q, equivalence and milli equivalence. So this is a way we can measure ion concentration in solutions. And it's just going to be in an equivalence per liter instead of a moles per liter, which is how we've typically talked about measuring solutions. And I actually want to show you why these are important after I define it. So an equivalent, what is an equivalent? It's the number of ions that carry 1 mole of charge. Okay, what the heck does that mean? 1 mole of charge. Okay, so it's all about the charges on ions. So do not overcomplicate this. You are able to recognize any charge on any ion. Calcium. What's the charge on calcium? Anybody know? +2. So as long as you can identify the charge on an ion, you can identify how many equivalents are present depending on the concentration of the ion. So aluminum has a +3. Okay, so we're focusing on the charge associated with ions. Okay, fluoride, it doesn't have to just be positive charge, by the way. It could be negative charge. Fluoride has a -1. Chloride has a -1. Oxygen would have a -2. So it doesn't matter if it's positive or negative. We're looking at the charge on ions and we're measuring the amount of charge. All right, so I want to prove to you that these are actually quite important. Why? Well, let me tell you a story really quick. When you have children, sometimes they throw up all over you. Did anybody get a stomach bug back like January, February? It was making its way, especially if you live in Conway. It was making its way. Well, it hit our house at the end of January, right at the end of January. We had just had COVID, by the way, and then the stomach bug hit our house. It was great timing. So my poor daughter, she's 2. She was 2.5 at the time. 2-year-olds just don't know how to tell you when they're about to throw up, right? So I was literally like watching her all night long to look for like anytime she'd start coughing, I just like hold her over a trash can. So I've never caught so much throw up in my life on me until I was a mom. But the day after she got done with all that, I gave her, anybody heard of like Pedialyte? So I actually brought a show and tell item to class today. I don't know what brand this is, but it's a pediatric electrolyte. You guys can see that. And I was actually looking at this box, and look right here. I'm gonna hold it really close to my camera. Can you see the units there? Are they blurry? Okay, what about now? Are they still blurry? Can you see them at all? No? What if I hold it out? Okay, it says MEQ. Would you look at that? Okay, obviously you know what MEQ is now. So any sort of electrolyte, obviously, why am I giving my daughter this? Because her body is deplenished of everything, right? Anytime you spend the night throwing up, your body is just deplenished. This can also happen in more serious cases. Third world countries that don't have proper sanitation or sewage systems, things like cholera are incredibly rampant, right? And when the body is depleted, because that can cause severe diarrhea or nausea and vomiting. And kiddos that experience this just because of the areas that they live in, their bodies, that's the number one cause, honestly, of like death among kiddos in certain countries that just don't have proper sewage systems. So there are ways to correct it, and it's called hydration therapy. So this can balance electrolyte levels when body is depleted. But there are ways to prevent it if we would just have proper sewage in countries like this, okay? So anyways, hydration therapy, you can look it up. But that's why you would, drink Gatorade or something like that after you're sick to replenish the electrolyte levels. Hunter says, I used to drink half a bottle of that after each match and I wasn't to get ready for the next one. It's a real deal. So it can apply to sports as well, and performance there, because we know our bodies have to have these electrolytes. So if we're thinking about the charge concentration here, if we're trying to measure an equivalent, if I have 1 mole of sodium cations, and we know each sodium cation has a +1 charge, how many equivalents is this? Okay, remember, one equivalent, an equivalent is one equivalent, has 1 mole of charge. So let's think about this. 1 mole of sodium cations would give you 1 mole of +1 charge. You just look at the charge. If I got 1 mole of it and it's a +1, then you have 1 mole of +1 charge. So that would be equal to 1 equivalent. What about something with a different charge? What about a mole of calcium? Or you could equally say a mole of oxygen, which would be -2. Again, it doesn't matter if it's plus or -2. I would have, because I have double the amount of charge, I would have 2 moles. You got to break it up into +1 charges. You're looking at +1 charges. So I would have 2 moles of +1 charge. So that would be 2 equivalents. Did I lose anybody there? So then if we have 0.5 mole of calcium, we have half the amount of calcium, same amount of charge on a calcium cation, but we have now only half a mole of it. So if 1 mole was 2 equivalents, half a mole should be how many equivalents? That means we would have 1 mole of +1 charge. And that brings us back down to 1 equivalent.
If you were doing oxygen, would it be -2 equivalent?
It's still you don't consider the plus or the minus. It's just because it doesn't say 1 mole of like positive charge. It's just charge in general. So positive or negative charges are just charges in this case. But it would still be, if it was oxygen, it would still be 2 equivalents in that case, because the charge on an individual oxygen anion is a -2. Did that answer your question, Madison?
Yes, ma'am. Thank you.
Okay. All right, so what we learned from this is 1 mole of sodium has the same quantity of charge as half a mole of calcium because the charge is double on a calcium cation. All right. And then I already introduced this in milli equivalents. Obviously, milli means there's 1,000 milli equivalents in one equivalent. Okay. Table 9.6 just shows you the necessary equivalent levels in, look, milli equivalents per liter for several different electrolytes in the blood. Not surprising that we need the most sodium and chloride, right? Okay. Let's do a few more practice problems with this just to make sure it hits home. And then we got to move on to talk about osmosis. That's the last thing. All right, how many equivalents of aluminum cations are obtained from 1 mole of aluminum plus 3 cations? How many equivalents of aluminum cations are obtained from 1 mole of aluminum plus 3 cations? So Kishan says, can you just multiply the charge by the number of moles? It's exactly right. It's exactly what you should be able to do. So if we have aluminum, we've got, if you want to break it down into +1 charges, you got +1, +1, +1, right? That adds up to +3. So if I have 1 mole of each of these, then yeah, I have technically 3 moles of +1 charge. Okay, so we can multiply that, the moles we have by the charge to get our total number of equivalents. So that I equals 3 equivalents. Okay, what about fluorine? We've got 1 mole of F minus. So it's a -1 over here, and we got 1 mole of it. So 1 times the -1, we should just have 1 equivalent. Okay, we've got 1 mole of -1 charge. Okay, but what if I had a compound? Okay, what if I think on your exam, not your exam, on your homework, with either osmosis or equivalence, it'll do something like this. What if we had CaCl2? What if I have 1 mole of that? How many equivalents? Oh, Kara says, can you scroll back up just a little bit? Where did you want me to scroll to? Oh, here. I'll keep that visible. If you have 1 mole of calcium chloride, then you're going to get 1 mole of +2 charge, which equals 2 moles of, I don't know what just happened. I think I accidentally wrote on an arrow, of +1 charge. So that is 2 equivalents just from the calcium, right? Because this is going to break up into, this is going to break up into Ca2 plus and 2 Cl minus. And then you're also going to have 2 moles of -1 charge from the chloride. So you get 2 equivalents from the calcium, 2 equivalents from the chloride. So total, you would have 4 equivalents, not just 3, because the calcium cation has a +2 charge. Does that make sense? That should be a Q, EQ. Bradley says you kind of lost me. All right, let's do that again. We got calcium chloride. That's going to break up into, says you are, y'all can't see my screen anymore, can you? I don't know what happened. Come on. Oh. All right, now are you good? We back? So that's going to break up into a calcium, which is a +2. And we actually answered this question earlier. 1 mole of calcium cations gives you 2 equivalents. That was a couple slides ago. And so I just wrote, we're going to have 1 mole of +2 charge, which is the same as saying 2 moles of +1 charge. So that is 2 equivalents just from the calcium. And then when you're looking at the chlorides, we have, for every 1 calcium, we get 2 chlorides because of this subscript 2 right here. And each chloride is a -1. So if we're going to have 2 moles of -1 charge from the chlorides, which is also 2 more equivalents. When you add all that up, 2 plus 2 is 4. Did that help, Bradley? Okay. All right, we got 10 minutes left. That's it. Okay, we gotta hurry. We're gonna skip this because we just don't have time for it, and it's not the main thing in chapter 9. We cannot skip osmosis though, so forget colligative properties of solutions. Let's go to osmosis. Okay, I need you guys to listen very quickly. And if I talk very fast in these next 10 minutes, know that this is recorded. Disclaimer, I'm probably gonna try to move quickly through this because osmosis is critical. You all have heard osmosis in your biology class, right? But it's not this. I wish it was. How many of you would actually sleep on your chemistry book if it would help? If this is the way knowledge was transferred, right? Too bad. Okay, what is osmosis then? It is the passage of solvent particles through a semi-permeable membrane separating 2 solutions of different concentration. I'm going to highlight the word solvent. We tend to focus on the solute. We measure the concentration of the solute particles in the solution. We've been talking about solute this whole time. So this kind of is a little bit antithetical to what we've been talking about. Now we're focusing on movement of solvent and we're measuring solvent. So it's the passage of, what is a semi-permeable membrane? What in our bodies have semi-permeable membranes? All of our cells, right? So this happens all the time. This is really, it's going on all the time in our bodies. So a little bit more about osmosis is it depends on the concentration of particles. We do not care about the identity of particles as much as we care about the concentration. So I'm just going to use blanket the word particle to identify any ions, okay? Because we don't care if it's a cation or an anion. We're just looking at how many particles. Yes, capillaries also have semi-permeable membranes, okay? And this is all about a gradient. You guys have heard the word gradient before, I bet, in biology, okay? How do gradients work? You have an area of high concentration, you have an area of low concentration. So when you have a gradient set up, I have to slow down, like spell the word out in my head sometimes. When you have a gradient, how's the solvent going to move? Okay, solvent moves from area of low concentration of particles to high concentration. Okay, we're talking about the concentration of particles, not the concentration of solvent. The solvent is what is moving, but it's moving from an area of low concentration of particles, stuff, ions, proteins, sugars, whatever's in our body, to a high concentration, okay? So it's always working, you can think of this, it's always working to dilute a high concentration. It's kind of always working to dilute. So we're going to talk about how that would apply to this picture down here at the bottom in just a second, but I want to actually write out an equation for how we measure osmolarity from a chemistry standpoint. It is just the number of moles of particles. Again, what does particles mean? Okay, it means things like glucose, things like ions, moles of particles per liter of solution. Moles of particles per liter. All right. So if we have 1 molar sodium chloride, we'll have a mole of sodium particles and a mole of chloride particles. We would get 2 osmoles per liter, all right, or 2 osmoles, 2 moles of particles per liter. If we have 1 molar glucose, which is a mole of glucose per liter, glucose does not break down into any other particles. It is the particle. So we would just have 1 osmol. Okay, we're gonna look at some more examples of that in a second. Okay, you got a picture down here with 3 osmoles on one side, 1 osmol on the other, based on the number of red dots you see. The red dots are the particles. Which way would the solvent move if osmosis was happening here? Would it move towards the left or towards the right? Uh-oh. Kitty says left. Kitty says right. Left, left, left. That's right. It's going to go from low towards high. So all the solvent is going to pass over this semi-permeable membrane to the air of the high side. So you get a picture that looks like this in the bottom. And now it would level out. Okay. The goal of a gradient here in osmosis is try to make the concentrations equal. So then you have 2 osmoles, if you've diluted the left side. All right, when that happens, you actually say now these solutions are isotonic. There's a word we use to characterize solutions that have the same osmolarity. That word is isotonic. But if you obviously can have solutions with higher and lower osmolarity, you have 2 other vocabulary words I want to introduce. I'm going to scroll back up for just a second. I know I'm moving fast. I'm so sorry. Let's look at the numbers we had up here, 3 osmol and 1 osmol. 3 osmoles higher, right? So we would call this hypertonic. 1 osmol is lower, so we call this hypotonic. So I want to make sure you guys understand this real quick. Let's launch another poll question. And I'm probably not going to give a ton of time on this one, but read this question. Solution A has an osmolarity of 3 osmoles. Solution B has an osmolarity of 5 osmoles. So solution A is what? Iso, hypo, or hypertonic compared. You're describing solution A. That's the one with the lower osmolarity. Compared to solution B, we would classify solution A as iso, hypo, or hypertonic. There's no water in that. Okay, I'm gonna end the poll real quick. I don't see the numbers really going up anymore. About 12 of you have not voted. Well, 8 of you. All right, here's what everybody said. Should be, that's right, hypotonic. Okay. Anything with a lower osmolarity is hypotonic compared to something else. All right. If it has higher osmolarity, we say, if I was asking you what solution B was, you'd say it's hypertonic compared to solution A. Makes sense? Questions on hypo and hyper? All right. So I know you have questions like this on your homework. So we're going to work the one I think is hardest, number 2. When calculating osmolarity, I'm going to highlight this. Ask yourself, how many particles or ions will this compound produce when it's dissolved? You don't care about the charge. Forget equivalence right now. That one's all about charges. Here, you're just looking at how many ions. So, for example, if I have 1 molar calcium chloride, I will get 1 mole per liter, because that's molarity, of the calcium. And then I will get 2 mole per liter of the Cl minus. Why did I say 2 mole per liter of that? Because I'm going to get 2 chlorides every time this dissolves. So it's going to dissolve into 3 ions total, 1 calcium and 2 Cl minuses, right? So if we add all of this up, it's going to be 3 moles of particles per liter, which is 3 osmoles. So again, just break it up into how many ions it produces. Calcium chloride is going to give you 3 ions, 2 anions and 1 cation. You don't care about the charges here. Then you just add all of that up. So what about glucose? Real quick. Glucose. If I've got 3 molar glucose, what's my osmolarity here? How many particles? So I got 3 moles of glucose particles per liter. Is that going to dissolve into anything? It's going to break apart in anything? Glucose, insulin, fructose, none of those biological molecules will. So we would just say this is 3 osmoles. Does that make sense? Okay. Hope so. I have 1 minute to do the remaining slide. Okay, I promise is the last one. Unfortunately, we're not going to get to osmosis and oxygen transport or dialysis, even though it applies and it's really cool stuff, but we'll stop here. But real quick, look at these blood cells. So if you have red blood cells in isotonic solution, that means the outside solution has the same concentration of particles as the inner solution of the red blood cell. That's how red blood cells should look. They kind of look like a donut shape, right? Well, when you have red blood cells in a hypotonic solution, that means the solution outside the red blood cells is a lower osmolarity. And in the red blood cell, it's a higher osmolarity. So remember, how does solution flow? From low to high. That's how the solvent flows. So that means all the surrounding fluid will rush into the red blood cell and then they swell up, like the picture that you see. Okay, because solvent always moves from low to high. Okay, what about red blood cells in hypertonic? That means the solution outside is a higher osmolarity than the solution inside the red blood cell. So when that's the case, the solution is going to rush, the solvent would rush out of the red blood cell into the surrounding area and it will shrivel up the red blood cells. Anybody ever heard of like sickle cell anemia? Okay, this happens in that sort of case because solvent, remember, always flows from low to high. All right, I'm past time, I'm sorry, but thanks for coming.